Yeah, that way. Okay, this is note-taking guide 5.11 for mathematical decision making for life. Today we're going to talk about something called probability distributions. And just like on the bell work when we drew those bar graphs, we're going to do the same kind of thing here. But let's take a look at this first example. It says, you are a space alien. You visit planet Earth and you abduct 97 chickens, 47 cows, and 77 humans. Then you randomly select one Earth creature from your sample to experiment on. Each creature has an equal probability of getting selected. Create a probability model to show how likely you are to select each type of Earth creature. So if anything, this is an interesting example, right? So we're going to find the probabilities of each one of those things happening. So well, first of all, let's find the total number of Earth creatures they took. So do the 97, the 47, and the 77, add those together, and get me that total. 221. I think I agree with you. Yep, 221. So we know there's 221 total that were abducted. So what's the probability of them picking a chicken randomly out of that 221? 97 out of 221. Okay, we're going to go 97 out of 221, and then we're also going to change that to a decimal point number. So can you do that as a decimal point number for me? Anybody? Thank you. So 0.44, or I guess if that third number was 7, we could go 0.45. Should we change it to 0.45? Because I can. Okay, next probability is for a cow. How many cows were there total? 47. Out of the total 221. Find that as a decimal point number for me. So 0.21. Okay. And then humans were 77 out of 221. And as a decimal point number, 0.34. Okay.
It could be 35.
Yeah, I think you could round that one up too. You want to go 4 or 5?
5.
5.
We always like more.
We always like to round up when we're supposed to. Okay, what I want you to notice right here is that if you add these up, will you add the 0.45, the 0.21, and the 0.35 together? Yeah, it adds up to 1, right? Or 100% of something happening. I think when you add this up, you actually get 100.1 because of our rounding. But those are rounding errors, right? Because we rounded things, we're going to not be exactly 100 or not exactly 1. And I meant to put 100% there because that actually adds up to 1.01 or 101% if we were looking, or 100, I still wrote that wrong. Anyways, it adds up right to the number 1, which is what we're trying to do today. We're trying to make sure that we've taken into account all of the probabilities that can happen for an item. And when we do that, it adds up to the number 1, which is 100%, okay? So what we're going to do today is we're going to find those probabilities. We're also going to graph them and decide if we make sure we have all of the probabilities accounted for, meaning they have to add up to the number 1. So let random variable x be defined as the number of heads obtained when flipping 2 coins. List your possible outcomes, then make a probability distribution table and graph for the random variable x. So what they're saying here happened is we flipped 2 coins. Now I'm going to do a tree diagram for that just to remind you what that would look like. So if I flipped 1 coin, I had a chance at a heads or a tails. Everybody agrees with me on that? Once I flip that second coin, the second coin, if the first one was heads, it could have been heads again. If the first one was heads, it could have been tails the second time, right? And then the same thing here. We would have heads and we have tails. So doing this chart helps me decide how many outcomes I have. I actually have an outcome that could have been heads, heads. I have an outcome that could have been heads, tails. Do you guys remember doing this from the very beginning of the chapter? I have an outcome that would have been tails, heads, and an outcome that would have been tails, tails. So how many total outcomes do I have? 4. When I'm doing my probabilities, my answer is going to be out of the number 4. Everybody's following me on that? Okay. So it told me that the probability that I was looking for was the number of heads. They told me that was my variable that I was going to be looking at. So how many times out of my 4 probabilities did I get 0 number of heads? 1, because I got tails, tails 1 time, right? So I'm going to go 1 out of 4 right here because I'm going to write my decimal point number and my probability here. What did you get for your decimal point number for 1 out of 4? Yeah, 0.25. Okay. Now again, we're looking at the number of heads. This time it says we have 1 head. So not that one because there's 2 heads there, but this one and this one both have just 1 head. So how many out of my 4? Yeah, which comes out to be what decimal point number? 0.5, right? Because 2 out of 4 is 50% or 0.5. Okay. And then the number of heads is 2. That happens 1 out of the 4 times, which is 0.25 again. What do you know about 0.25, 0.5, and 0.25? What do they add up to be? 1. So we know that we found all of the ways that that could happen. That just is a way to double check our math and make sure that we know that we have all of the possibilities accounted for. Does that kind of make sense? So now that we have those, we're just going to graph them. So here we have, and just like on the bell work, we're going to do a bar graph. So at 0, we're going to be up to 0.25, which is like right here. So I'm just going to do my bar graph around like this. And I've been liking to just label inside how far I'm really up, so that if later I have to go back and answer a question about it, I can see where I meant to be. Because clearly I'm up a little bit higher than I should have been, but 0.25. At 1, we're going to be up to 0.5. And then at 2, I'm back down to 0.25. Okay. Questions on how I did that? Does anybody know what kind of distribution this would be called when it kind of makes a curve up and down like this? No? It's called normal. It's also been called a bell curve before, right? But this is called a normal distribution. And we're going to, not get really deep into those, but if you had a question that said, is this a normal distribution? You would be looking for that up and down pattern that happens equally on both sides. Okay? Next problem. Let random variable x be defined as the number that lands up when we're rolling 1 die. List your possible outcomes, then make a probability distribution table and graph for the random variable x. So you roll a dice. You have a chance of getting 1, 2, 3, 4, 5, and 6, right? That's your chances. That's your possible outcomes. So how many times, or what's the probability of rolling a 1? 1 out of 6. Probability of rolling a 2? 1 out of 6. A 3, a 4, a 5, and a 6. Do they have equal probabilities this time?
Yes.
They do, right? So what's the decimal point number for 1 out of 6?
Well, 0.16.
Yeah, 0.16, or I rounded mine to 0.17. Did you guys look at it? Should it be rounded to 0.17?
Yeah.
Yeah. So 0.17 all the way down.
Is that gonna throw it out?
Well, it's going to be a little bit higher than 1 because we rounded, but that's going to be a rounding error. When I added those up, I got 1.02, which means I accounted for all my probabilities and there was just a rounding error. Then we're just going to graph those, okay? Which, that should be pretty easy to graph, right? And actually, when I did it on my paper today earlier, I totally was lazy and I went across like this at what I called 0.17. And then I just drew my bars down like this because I was really lazy. And I'm like, oh, at 1 I'm 0.17, at 2 I'm 0.17, at 3 I'm 0.17, at 4 I'm 0.17, at 5 I'm 0.17, and at 6, guess what, you guys? I'm still at 0.17, right? So you could have done it that way, or you could have drawn individual bars if you wanted to, but they would all be exactly the same height because the probabilities are exactly the same, okay? This would be called evenly distributed. Does that make sense to everybody that that's even, clear across the board, right? So this would be evenly distributed. I'm not going to ask you about these later, which is why I didn't put them on the note-taking guide. I'm just trying to give you some information in case you ever have to take a real probability or statistics class. They will dwell a lot on those distributions and what their names are, okay? Next experiment here, it says let random variable x be defined as the sum of the two dice. What does sum mean?
Add.
Yeah. So we're rolling two dice and we're adding them together, okay? Make a probability distribution table and a graph for the random variable x. I actually gave you what could happen when you roll two dice. You could get a 1 and a 1, which adds to be the number 2. So do you see how I didn't start my chart with the number 1? I started it with 2 because it's the first possible outcome that we could have. So how many total outcomes do we have when we roll two dice?
A lot.
A lot. Count them or multiply, right? 6 by 6 is how many? 36. There's 36 possible outcomes. How many possible times can you get 2? Just one.
Really?
Yeah, just one time.
Wait, so you can get 2 ones?
Yep.
Yeah.
Yep. That's the only way that you can add to the number 2 on two dice rolls is a 1 and a 1. So your probability is 1 out of 36. But again, I want to go decimal point numbers. So when you do 1 divided by 36, you get 0.03. Okay. Then we're going to go and find the probability that they can add to 3. Now, if you look at this chart, we just used those 2's already. Can you see that the only way you can get to 3 is if you rolled a 2 and a 1, or if you rolled a 1 and a 2. So here's my 3's. There's 2 out of 36 of them there, which as a decimal point number, 2 out of 36 is 0.06. Right? Okay, are you seeing how this chart's going to work? Do you see how if we look diagonally, it has all the possible outcomes for adding to a certain number? So this time we're looking for adding to 4. So that adds to 4, that adds to 4, and that adds to 4. So how many possible outcomes are there? 3 out of the total 36. And 3 out of the 36 is how many as a decimal point number? 0.08. I don't know, is that what you guys got?
Yeah.
What about the number 5? How many possible chances do you have of adding to 5? 4 out of 36. And 4 divided by 36 is 0.11. How many chances to roll a 6?
5.
Yeah, 5 out of 36. And that comes out to be what decimal point number? Is it 0.14? I didn't hear what you said.
Point
Oh yeah, let's go 0.14 just for the heck of it. Okay, possible number of outcomes for the number 7, adding to the number 7.
6.
Yeah, 6 out of 36, which is going to be 0.17. What do you think is going to happen here on this downside? Yeah, it is. Does it go down the same way it went up?
Yes.
I don't know. So, well, let's just check it and see. How many chances at 8 are we going to have?
7. 5.
5. Then how many? 4.
4. 3.
Then 3. Then 2. Then 1. Is that the same way it went up? So are you guys all right if we don't like use all of our time to figure those out again and we just copy the opposite direction? So what's our next one gonna be? 0.14.
Yep.
Then what?
11.
Then 8.
8.
Then 6. And then 3. When I added those all up, I got 1.01. Again, that was a rounding error. It's because we rounded those numbers. If we would have left those numbers unrounded, we would have come up with exactly 1. Okay? But that's close enough. That tells us we didn't count wrong, right? We know that we're close enough that we didn't count wrong. And then we're just going to graph that. So when our answer is 2, we're up at 0.03. So we're not up very far. And then I'm going to go over and do 12 also. Is that okay if I do 12 at the same time? Because aren't they the same thing? And then at 3, I'm 0.06. I'm also that at 11, aren't I? And then at 4, I'm 0.08, which, you know, doing the best I can here. Which I'm also over at 10 at that same number. And then I'm 0.11. Then 0.14. And the middle one's up at 0.17.
Doesn't this graph have a name to it?
It does. Do you remember what I said it was?
Normal?
This is normal. Definitely normal. Because it goes up and down. It's also called the bell curve. And it kind of has this really pretty up and down movement to it. And it flattens out over on both sides. It's called the bell curve. It's called a normal distribution. Which we're going to learn how to do some math on next unit. That will be super fun. So, but that's what it looks like. Questions on how we did that? Still not hard, right? This is just like a little bit time-consuming math, but not really hard math. Okay. Next problem. So this is, now we're just going to kind of manipulate the numbers here for a minute. So it says, Hugo plans to buy packs of baseball cards until he gets the card of his favorite player, but he only has enough money to buy at most 4 packs. Let the random variable x be the number of packs of cards Hugo buys. Here is the probability distribution for x. So look for just a minute. They gave us the probability of 1 pack, 2 packs, 3 packs. They didn't give us the probability of 4 packs. Would you be able to find out that probability for me with what information that I keep telling you repeatedly?
Yeah.
Do you remember what they have to add up to be?
100.
Yeah, or 1, right? Because they're decimal point numbers. The probabilities all have to add up to be the number 1. So can you take the number 1 and subtract these 3 values off of it and figure out what that probability has to be? That is right. Thank you. 0.512. So my probability for that 4th deck is 0.512. Okay. Now we're going to ask you questions about this probability chart. It says, find the probability that x is greater than or equal to 2. Well, it's equal to 2 right here at 0.16. Do you agree with me on that? And then greater than would be 0.128 and 0.512. So I'm really just going to grab those probabilities and add them together. That's going to give me the probability of greater than or equal to 2. So I went to 2 and I did everything greater. I add those together and that's my total probability. And what's that number going to be?
All 3 of those?
Yeah, all 3 of those.
50.
Yeah, 0.8 is your answer. Okay, so that wasn't hard either, right? Grabbing probabilities off of the chart. This next problem works exactly the same way, just with a lot more numbers, some extra questions. So it says, according to the 2005 census, the probabilities of having 2, 3, 4, 5, 6, and 7 plus members in your family is 0.42, 0.228, 0.209, 0.092, 0.032, 0.019, respectively. Does anybody know what it means when it says respectively? It means they match up in that order. So the number 2 has to go with the first number, the 0.42. Does that make sense? Respectively means in the same order. So when I did this chart, you guys, on this note-taking guide, I actually didn't put enough boxes. We have to add one more box over here at the end. So sorry about that, but that's what I do, make mistakes. I just do. So 2, 3, 4, 5, 6. Did you see me say 6 and write 7? I don't know. 6. And then 7 plus go along as my x values. Then I'm just going to write these in the same order they were given to me underneath the numbers they go with. So 0.42, 0.228, 0.209, 0.092, 0.032, and 0.019. So all I did was write those out so that they were easily readable in the chart so that I can answer the questions about them. Again, respectively just means in the same order they were given. Okay, so then A says, what's the probability of